Good morning, everyone. I'm James from Huawei Cloud Reliability Lab.
Hi, I'm Jayaganesh from the I'm also from the Huawei Ireland Research Center as well, Cloud Reliability Lab as well.
Yeah, I'm glad to be the first presentation today. So hope you're not as sleepy as me. So. Okay, so today we're going to talk about the lessons we learned from building our level 4 load balancer called HyperRouter. This is the rough agenda, not exactly reflecting the slides. So basically, we're going to talk about the scale of Huawei Cloud and our deterministic operation framework, and then high-level introduction about global load balancing platform, and then dive deeper into our level 4 load balancing from data plane to control plane, including some operational excellence lessons. So let's have a quick look at the scale of the Huawei Cloud. So Huawei Cloud is relatively new to comparing to other cloud providers. So many people may think Huawei only build hardware, like switch or even mobile phones, but actually we also build cloud. We already have more than 33 public regions, also many private regions, and it's still growing fast, about 20% per year. So in order to ensure the reliability of cloud services, we introduced a framework called a deterministic operation. So it's not just for operation. Basically, it's a systematic framework to ensure the system reliability from end to end, from design phase to verification, testing, to change management, and also data operation, and to ensure the services have predictable performance, scalability, and also have certainty for disaster recovery as well. Is also kind of working backwards mindset. So for example, when we start a new service, we have to think about how the system will be operated, how to deal with disaster recovery, all those things at the very beginning. So we also build many common services and platform services. For example, the global load balancing service is one of the critical cornerstone of this whole deterministic operation framework. For example, it provides cross-region load balancing. It also cross-AZ, cross-cluster load balancing flow automatically. So just in case somebody don't know what is load balancer, I hope most of you know that. But so basically, a load balancer is a system itself that distributes networking traffic across multiple backend servers to ensure the reliability, availability, scalability of a performance of another system. So that's why today we are going to share. Share about experience about building a load balancer service. It's a level 4. We call it HyperRouter. So we're not going to talk about how to use a load balancer. It's a software load balancer. I guess most modern load balancers are based on software based. It's not. It may still have some hardware based load balancer, but it's not not within the scope we're talking about. Our system was built for large-scale multi-tenancy platform as a cloud provider. So that means some of those experience not apply for all scenarios, but I hope it could be also interesting to learn. Yeah. So the interesting question would be load balancer as the reliability foundation for other services. So how could we ensure or guarantee the reliability of the load balancer itself? That's exactly the problem we're solving in our whole load balancing platform. Actually, last year in the SREcon, we talked about our level 7 data plane. It's called Orin. So it's also open sourced. If you're interested, you can look at the GitHub code. And so today we're going to talk about the level 4, our HyperRouter, the level 4 load balancer. So before, as a platform, so even though we have different layers, but we always have to have a holistic view before we start design a system. So co-design, that's why we have to share about how co-design level 4 and level 7 load balancing. So the first question you may be wondering why we need a level 4. Always, mostly, at least most of the time, you need a level 4 load balancer in front of your level 7. So the primary reason is normally the level 7 LB is not resilient to the, for example, node failure. Usually, for example, you use Nginx or Envoy or Ring. Then once one of the node fails, it may mess up many TCP connections because it's not resilient to the ECMP. Yeah, so I mentioned two related concept here. If you're not familiar, I have a very quick definition here. Uncast, basically, you kind of sharing the same IP address from multiple servers. So you have 100, even more. They're advertising the same IP address based on BGP or other routing protocols. And the related concept is called ECMP. That means for the router EDC, for one IP address, it has multiple destinations, how the router should pick one of the server. Then normally it's just based on very simple hashing on the 512. 512 means the source IP, source ports, and protocol, and destination IP and destination ports. So that's why we usually have, in front of level 7, we have the level 4. And usually level 7 is more stateful. For example, you do TLS termination, HTTP header, and body processing, and so on. And the level 4 we designed to be more stateless for just focus on the packet forwarding. And so in order to ensure the scalability, we use consistent hashing for the load balancing and connection tracking to ensure the issues I mentioned. If suppose there's some failures on the level 7 or have scaling up, scale down, or the connection tracking table ensure the TCP flow works for the already established connections. So before we design HyperRouter, we already have a system level 4 and level 4 load balancer, which is based on LVS. It implements for so how it works, basically the level 4 get a packet and forward to the level 7 and then to the microservices and then get back to the level 7 and get back to the level 4. But there's a problem with this approach. So suppose you just think about the HTTP gets is where the request is very small, maybe just a few bytes of requests, but response could be any size. It could be just a few bytes to a few megabytes to even gigabytes. So in this case, most of the time, the level 4 don't need to do any process for those response, or the level 4 should not care about the response for the in this case, just wasting resources, and also make the level 4 is not so scalable. Yeah, that's why when we design the level 4, we propose to only support the direct server return. That means we only focus on the ingress traffic load balancing for level 7. And then that means we know our level 7 have to do just return the response through the default gateway to clients. Yeah, this is that's why we have the co-design together, because it will simplify our level 4 as well. Yeah, so the first lesson would be the co-design. The related systems like the level 4 and level 7 in our case could be reduced overall capacity and also improve the overall reliability of the whole system. Yeah. Now let's dive deeper into our HyperRouter. We have 4 very simple but not easy objectives. Similar to most distributed systems, need high performance, high scalability, high reliability, and also future-proof. In this specific case, the high performance means we need to reach close to line rate speed on average packet size. So we're not seeing for all type of packet size. For smaller one, maybe more challenge to reach, non-reach. And we also have the save cost. We don't want to have a lot of resources to achieve to minimize the cost. For example, that's why we may have to process more than 10 million packets per second per CPU core. And we also have to minimize the overhead because of load balance. So any backend services don't expect increase the latency because you're using load balance, especially level 4, right? So we may have to process packet at nanoseconds. And scalability, yeah, that's quite easy to understand. As I mentioned, the scale of the Huawei cloud, and we're also growing, so we have to scale up our clusters to meet new requirements, the increasing traffic. And we have more deployed to across new data centers, new AZs. For reliability, it's more challenging because customer always expecting almost zero downtime for cloud services, especially for load balancers. So you use most customers, even they know the SRE is only 4 line or even 5 line, but they don't even expect any downtime. So that's why we have to try our best to ensure the high availability during our daily operation, and also should be resilient to partial failures, for example, networking failure or hardware failure. And future-proof, so the system should be evolvable to adding new features, to adapt to new hardwares, for example, to leverage new capabilities provided by NICs, or some new scenarios. So we don't want to start a new system a few years later from scratch, and so that's the high-level objective. And yeah, the high-level architecture is quite simple. We have data plane and control plane. Data plane focuses on the packet processing for load balancing, and then control planes basically providing the APIs and also the cluster management of the data plane, configuration management, and so on. For the data plane, in each node, the process is also, the high-level process is pretty simple. So basically, once we get a packet from the NIC, sorry, there's some mistake here. So it's from the RSQ, it's the receive queue. And then we need to get based on the IP and TCP and UDP header to match if we have any virtual IP configured for a specific load balancer, and do we have any national config for the specific and for the packet. And then we have to pick one of the backend from, let's say, Tang or even more backend based on the consistent hashing or any other simple algorithm like run Ruby, which is also commonly used. And then we do packet encapsulation. Encapsulation here is because as I mentioned, we support only direct serve return. That means we have to encapsulate the original packet into another one, another layer similar to the VX9, or use IP or GUE encapsulation, and then forward back to the NIC. So our system implemented based on Linux. So the straightforward approach would be how to implement based on achieve the high performance in Linux kernel. But Linux kernel networking stack is designed for general purpose. It's very good at this, but it's very flexible, but it's not optimized for our use case for extremely low latency and high performance, for example, because the context switch between user space and kernel space and our memory allocation. When the NIC get a packet, and then Linux kernel has to allocate called socket buffer and something like this. So it may be possible to achieve near non-read speed with Linux kernel, but you may need more intensive tuning, and also it costs more CPU cycles. So here is a high-level structure of the Linux kernel. It has the different layers, the drive layers. So once you get package from the input pass forward to the user space, and then back to the NIC. Or you may have forwarding pass. That's how it usually works. But actually, Linux provides a kind of native kernel bypassing approach. So you could process the packet as early as possible. If you don't really need complex, depends on the TCP/IP stack provided by Linux kernel. It's called XDP. So you could use the eBPF program to run to do the also make very simple decision based on the header to do you should forward or you should drop or you should just pass to the Linux kernel. So it's basically a framework that makes possible to perform high-speed packet processing in the user space, in the kernel space. Yeah, so most of the Linux kernel native version support that natively. That is good parts. And also is CPU efficiency. It met our requirements. But it comes with limitations because it's running based on eBPF and also in the kernel space with limited programming model. So it may not able to process. So it's not easy to extend to supporting multiple NICs, for example. And XDP program, it has to attach to each NIC instead of processing one application to deal with multiple NIC. For us, it's kind of hard requirements. We have to support at least 2 NICs because we have for each servers, most of the servers we have 2 TOR. That means we need to connect to 2 TORs for advertising to process the packet. And another common used framework called DPDK, which is a full user space framework to so basically take over the NIC and process the packet through the DMA, and then it's based on the polling mode to process packet fully in user space. So the benefits is you have full control in user space, and it's natively supporting multiple NICs. And it also management with future page is very efficient. But the downside would be you need dedicated NICs and CPU cores. So once the DPDK take over the NIC, you cannot reuse that for any other purpose. Your system cannot see the NIC anymore. And then it's always using polling mode. Other mode exists, but it's not for high performance purpose. So that means it's always using 100% CPU, even just no traffic. So this is kind of one-way door decision we have to make, and how to make this trade-off for long term. So that's why, based on our requirements, then we finally think this way is acceptable in our case. We need for long term for future flexibility. It's okay we have dedicated NIC. We have additional NIC for management purpose. And the CPU, we don't expect our servers running without traffic. So yeah, we have to make a trade-off here. Yeah, so basically, and then the lesson we learned would be user space kernel bypass enable. You could develop a feature-rich, ultra-low latency deep plane, but it limits the reuse hardware and kernel capabilities. So you have to so basically use the double-edged sword carefully. And then the next part I'm going to talk about would be the self-healing and isolation as the first cost design principle. So our deep plane or the hardware may go wrong at any time. So we have to design for failure. So that we have a self-health tracking mechanism. One of the components for example, in our data plane node, we have controller. It can collect metrics from the data plane, from the BGP speakers, also the backend based on backend health tracking. So it make decision, for example, if we see high rate of error rates in our NIC, we may think there's some problem with the hardware. We have to isolate the node by itself. So in order to isolate the node more reliably, so one of the approach would be we just withdraw the BGP from the node, then the BGP router will never see one of the node. But there's a problem there would be if we have a bug or there's a false positive, then we make all the whole deep plane clusters withdraw the BGP, and then even though there's traffic coming, even the load may be healthy, but we cannot process the packet. So in order to avoid this issue, we instead of withdraw the BGP, we just appending the AS number in the AS path. So this way we'll make the BGP router, it will see, usually it's based on the length of the AS path. In this case, the first node has longer AS path, so the traffic will be routed to the other two nodes. So in this case, the only traffic only go to node 2 and node 3. And suppose we made a mistake and the false positive, all the nodes isolated themselves. And then in this case, all the nodes will get traffic as normal. So that's the way we make the isolation more reliable. So this is just an example to showing that how we were doing self-healing isolation as the first principle. Then so we could leverage the natures or the system properties so instead of treating as afterthoughts, then we need to add some self-healing mechanism later. So it will be much easier to leverage those properties. Yeah, now I'm hand over to Jayaganesh to share the rest of those, the system.
All right, so far we have seen about the whole aspects of data plane, and now we'll be looking into the specifics of the of the control plane. And like the data plane, we also have a lot of constraints, and we need to pretty much work around them. One of the constraints we have here is we want to minimize the pretty much external dependency. That's one. The most important of all is it should be resilient to network partition. And also similar to the data plane, it should also be self-healing. In any centralized system, which it will be pretty much not susceptible to any network partition, pretty much following the normal cap theorem, where if you have consistency, you cannot have partition tolerance, or if you have partition tolerance, you cannot have consistency for the same given availability. So in this specific case, because the network partition is like super important to us, because this is a level 4 load balancer, which is going to sit at the base of the whole stack. So if at all we have any network partition, we want the whole stack to still work. For that, we chose to go for a system which is decentralized and can lead to a consistency which is not strongly consistent, but it can become slow / eventually consistent. One. For people who don't know what is P2P network, it's basically a kind of decentralized system where each node holds a small shard of data, right? So we made a small variance to the standard P2P network. We'll just kind of go through that in a bit. So the standard approach is that every node will hold a small, it will be holding a small shard of data. We made a modification so that every node will actually hold all the data. And eventual consistency will be achieved through those gossip protocol. In case of conflicts, we will be having versioning, which will be setting those precedents for us. Every node will be connected to every other node. So it will be a bond-based mesh communication by using bidirectional gRPC. It's a logical step from here that when you have multiple nodes and they're all getting connected one by one, you'll be forming a strongly connected system, which we will be referring to as islands. And you'll be having multiple of these islands, which will be linked via weak network connections. So think of it like inter-regional connections and so on. The network partition across these weak connections is still fine because every single island has a strong consistency within it. Another thing is it should be scalable and also balanced. So when a new data pretty much comes in, it can reach across all the nodes within a given island in like the log of the number of the nodes. This is important because when you have eventual consistency, you want the number of hops to be as limited as possible because you don't want the delay to be long enough. As mentioned before, we want it to be self-healing, so it should also be resilient to flaky networks. So the stack we put together in this case was the basic persistent layer, which will be the kind of local disk, on top of which we'll be having this. So we'll be having this key value system. And on top of this key value semantics, we'll be having the bond-based mesh communication, which is the whole communication layer in some sense, on top of which we'll be stacking the actual application layer node level details. So if you had seen in the last slide, we had different types of nodes. So you pretty much had the controller, health checker, and so on. So each of these have their own node-specific attributes. That will be the pretty much top of the layer application layer. So this worked for us. And this was pretty scalable inside it was pretty scalable inside the system as well. So the lesson we learned here is when you want to minimize the pretty much external dependency, going for a decentralized architecture is pretty useful. Because it's a new design, it's a new variant of P2P, we also wanted to make sure it is formally verified. We have a formal methods verification team within Huawei, within the Huawei Ireland Research Center. So if you are interested, you can speak to us afterwards as well. They rigorously verified the whole system specifications. They actually discovered a bug, which we weren't able to catch even after our exhaustive unit integration tests as well. And the bug was that in the bond communication, to build a bond, there could be sometimes it could be like a pretty much unpredictable number of retries which happens. So we were able to capture that with the formal verifications. Great. So now we have covered the whole data plane / control plane. The obvious next question is operational excellence. James spoke about this last year as well, about decreasing the overall blast radius. In a large-scale distributed system, especially when it is multi-tenant and this is the bedrock of the whole stack, it is important that if any failure happens, you contain it to the least blast radius. So cell-based architecture is a very well-known architecture. We made use of that. And also there is the shuffle sharding approach. AWS has a paper on this as well. We'll just quickly go over it and why it actually helps us. So in a static sharding approach, if you have, let's say, a total of pretty much 10 nodes, and you have a virtual shard where you pick every 2 nodes per shard. So you'll pretty much be having 5 shards, right? And if one shard goes down, it has a 1/5 impact on the user, which is like a 20% impact on all the tenants / all the traffic. If you compare this with the shuffle sharding approach, it's a bit different, where for every virtual shard, you randomly take 2 nodes, and they will be serving the shard. So in this case, we chose pretty much every shard to have 2 nodes. So you will pretty much have NC2, which is in this case total of 45. So 45 different shards, or you will have 45 different virtual shards in the sense. And if one shard goes down, the impact is just 1/45. And that works pretty well in this case because in this specific example, if you see that the cell 1 and the cell 2 are down, the virtual shard 2 will still work because the cell 3 is still not affected. So overall, we can decrease the blast radius by about 1/10. And hence, cell-based architecture by using shuffle sharding is a very powerful approach to decrease your blast radius overall. So we have the data plane, we have the control plane, we have the operational excellence. How do you know if these things all work together? Which brings us to the part of observability. There are 3 main aspects. One is what signals you need, what signals would tell you that you are actually performing well. Second is in this new day and age of frameworks, you already have a lot of by default configurations which will give you a lot of pre-built metrics those signals. In a list of predefined signals, how do you filter out those which are important to you? And if a signal misbehaves or if its behavior changes, how do you track it down to the actual root cause, be it your code level implementation changes or production level implementation changes? So for this, we use the framework of critical user journey, CUJ, which is a sequence of those essential actions we need to take to achieve a particular task. So if you think about the whole framework now, the CUJ is the top layer on which you start. CUJs will then advise on the signals you would need. Signals would then mean what instrumentation, implementation you need to do, and they all will sit on a bedrock of the whole observability platform, which will take care of your storage, /metrics, logs, traces, correlations, /context propagation, and all the basic infrastructure you would need for that. A small concrete example of how we use this within the level 4 load balancer. There are two main paths. One is the external user who will be using the data plane path. So they will be asking for a virtual IP to be resolved. And that virtual IP should be resolved by the physical backends, and then we need to pretty much return the response. That's one. In terms of the operator journey, for the internal maintainer who will be able to update those load balancer configurations, if they update the load balancer configuration, it should propagate all the way to be at the end populated onto the BGP. So these are the two major journeys for this specific system. We'll quickly go over the example of this control plane. So we first specifically wrote down the whole specific journey. The system receives the load balancer configuration from an system and then populates the virtual load balancer routes onto the BGP. From this, because it's an end-to-end path / you need to pretty much trace the route, we built tracing on top of it. And the tracing will give you those traces from which we wanted metrics / signals. So we use the span connector metrics to convert them to metrics so that we will be able to use some aggregation on top of them, and we can also pretty much alarm on them if necessary. From these signals, we were able to achieve two major tasks. One, we were able to understand the performance of the system for this specific user journey. Two, we were able to get a component level breakdown of this journey, and we were able to know the bottlenecks of this whole journey as well. Interestingly, we also had another use, which is that the data plane is very hard to monitor. Even though we use DPDK, and like DPDK has its own suite of monitoring, the DPDK monitoring doesn't give you internal information about the system in terms of the latency and so on. But here, because the path flows through the data plane, we were able to exactly pinpoint the data plane latency, data plane based correctness. And the user feedback, because it's going to be used by our own developers, the user feedback was that they have much more insights onto the system, which they were not able to get before. And in fact, we were able to use it internally, and we were able to make good use of it to have like actual understanding of those systems, and like we were able to discuss about what are the next improvements we should probably do as well. So the final lesson we learned is a CUJ based approach is a very strong, powerful framework to finally achieve user-centric observability. Now, just to recap on the last 6 lessons we learned. So 1, level 4, level 7 load balancers work together. And the user space kernel bypass is a very powerful technique. Self-healing and isolation should be a first-class design principle, and it should not be some afterthought. A decentralized architecture by using peer-to-peer is a very strong choice when you want to minimize those external dependencies. Cell-based architecture by using shuffle sharding is also very good if you want to decrease the blast radius. CUJ is a very, very powerful framework if you want to achieve user-centric observability. Great, thank you. So that's a talk. Now we can take some questions.